Effects of very short rest periods on hormonal responses to resistance exercises in men. Rahman Rahimi, Mohammed Kaderi, Hassan Farazi, and Saeed Borajerdi, Department of Physical Education and Sports Science, University of Kurdistan, Sanandaj, Iran. We're going to skip the abstract and go straight to the introduction today. Resistance exercise, RE, stimulates the release of different anabolic hormones, especially growth hormone, G8, and testosterone, TS. The anabolic hormones invoke the muscle protein synthesis. Therefore, RE enforces the access to muscle strength and hypertrophy. Because of important functions of anabolic hormones, there have been studied different approaches to increase the interaction between sport activities and endocrine glands. Resistance exercise-induced elevations in the G8 and TS concentrations have been shown to be influenced by the RE variables originally defined by Kraemer, including the number of training sets, number of repetitions, training intensity, training volume, and rest between sets. Among these variables, rest between sets in resistance training has been special importance, that is defined as the time period between the end of the training set and the commencement of the next set, so the body condition of the individual approach the physiological stance before the activity. The amount of rest between sets affects the metabolism, cardiovascular function, hormonal response, and also the number of repetitions in subsequent sets. Short rest periods are typically recommended for the RE programs designed to maximize muscle hypertrophy, because short rest periods augment the GH response when compared with long rest periods. In addition, previous research studies have shown that 1 minute rest between sets increased GH concentration compared to 3-minute rest in young men and women. Borajerdi and Rahimi have observed 15% significant increase in serum GH concentrations in RT with 10 repetition maximum, 10 RM, with 1 minute rest between sets compared with 3 minutes. Also, RE and 5 RM and 3-minute rest between sets led to a significant increase in TS. In addition, RE to failure and not to failure have different effects on hormonal responses and training volume. Muscular failure can be defined as the point the set is ended and a period of rest ensues to allow the resynthesis of adenosine 3-phosphate, ATP, and clearance of fatigue producing substances, e.g. hydrogen ions. Resistance exercise sets to failure might be most beneficial when programs are structured for increases in strength and hypertrophy. These adaptations attribute to greater activation of motor units that are capable of the greatest increase in strength and hypertrophy and secretion of growth promoting hormone. Therefore, in the present study, RE protocols were performed to failure in each set. Nonetheless, the previous research studies have examined acute hormonal responses to RE with a specific number of repetitions, 5 RM, 10 RM, and rest periods ranging from 1 minute to 5 minutes between resistance training sets. So the aim of the present study was to examine the acute GH and TS responses in a RE protocol to failure with 85% of 1 RM load and very short difference rest intervals of 60, 90, and 120 seconds between sets. Methods. Experimental approach to the problem. The acute hormonal response of 3 resistance training protocols differing by rest periods between sets, 60, 90, and 120 seconds, were studied with 10 recreationally resistance trained men. Loading protocols were performed to failure and expected to lead to large acute hormonal responses. We've hypothesized that when using short rest periods between sets in resistance training to failure, maximum repetitions per set, the endocrine response should be larger along with a greater metabolic stress, lactic acid, than that of long rest periods between sets. Subjects. 10 experienced resistance-trained college-aged men aged 22 plus or minus 2 years, weight 84 plus or minus 8 kilograms, and at least 1 year of RE experience volunteered for this study. Subjects were informed of the experimental risk and they signed an informed consent document before the investigation. The Institutional Review Board of the university approved the research protocol. Subjects were on their ordinary diet, not permitted to use nutritional supplementation, and did not consume anabolic steroids or any other anabolic agents known to increase performance. Experimental design. The subjects were familiarized with the experimental testing procedures during a control day about 1 week before the actual measurements. Resistance load verification for the experimental bench press and half squat exercises were also determined. All the subjects went through 3 strength exercise trials of different rest intervals between sets. The strength exercise lasted between 9 a.m. to 11 a.m. hours, and to avoid any potential carryover effects, the threats of internal validity, each of the 3 protocols was performed in a counterbalance order by all 10 participants. At least 48 hours, but not more than 72 hours of recovery time was allowed between each training session. During the control day, 3 blood samples were obtained from each subject. 1 blood sample was drawn in the morning after 12 hours of fasting and approximately 8 hours of sleep for determination of basal serum hormone concentration. The 2 blood samples were also drawn within a half hour without exercise at the same time of the day that each subject would later undertake his heavy resistance loading protocols of normal diurnal variation of serum hormone concentrations. During the exercise session, blood samples 5 milliliters were drawn from an antecubital vein into 10 milliliter serum vacutainer tubes at pre-exercise T0, immediately post T1, and 30 minutes post T30. Exercise for measurement of serum GH, TH, and blood lactate concentrations. The experimental design comprised of 3 separate sessions of the RE protocol. Subjects were assigned in a random order at the rest interval of 60 seconds, P60, 90 seconds, P90, or 120 seconds, P120, between sets. The RE session consisted of 4 sets of squat and bench press to failure using 85% of 1RM with a 4-minute recovery between the exercise. Strength testing. Lower and upper body maximum strength was assessed by using 1RM actions. Warm-up consisted of a set of 5 repetitions at the loads of 40 through 50% of the perceived maximum. In the half squat 1RM, the shoulders were in contact with the bar and the starting knee angle was 90 degrees. On command, the subjects performed a concentric extension as fast as possible of the leg muscle, starting from the flexion position to reach the full extension of 180 against the resistance. The trunk was kept as straight as possible. A security belt was used by all subjects. All the tests were performed in a squatting apparatus in which the barbell was attached to both ends with the linear bearings on 2 vertical bars, allowing only vertical movements. During the 1RM bench press test, the subject was instructed to perform from the starting position a purely concentric action, maintaining the shoulders back in a 90-degree abducted position to ensure consistency of the shoulder and the elbow joints throughout the testing movement. An attempt was considered successful when the movement was completed through a full range of motion without deviating from the proper technique and form. Spotters were present to provide verbal encouragement and safety for the subjects. To ensure that all subjects were moving approximately the same velocity for each repetition, each set was timed using a handheld stopwatch. The spotters called out a cadence for the eccentric and concentric phases of each repetition. The repetition velocity consisted of a 3-second eccentric phase followed by a 1-second concentric phase. During the next 3 testing sessions, 4 sets of the squat and bench press were performed with a 60, 90, or 120-second rest interval between sets. A counterbalance procedure was used to determine the sets. The order of the rest intervals between sets for each testing session. Subjects were allowed to continue with the normal workouts throughout the duration of the study with the following exceptions. Subjects were instructed not to perform training 48 hours before the testing session, and subjects were instructed not to change their eating patterns during the study. The values for 1RM were 105.62 plus or minus 18 kilograms for bench press, and 106.31 plus or minus 19.71 kilograms for squat. Hormonal analysis. Blood samples, 5 milliliters, were drawn from the antecubital vein into 10 milliliters serum vacutainer tubes, and after approximately 45 minutes, serum tubes were configured at 3,000 RPMs for 10 minutes at room temperature. Serums were separated from blood cells and stored at -20 Celsius until analyzed. Serum TS and GH concentrations were determined using enzyme-linked immunosorbent assay, DRG Instruments GmbH, Germany, division of DRG International Incorporated, Hamburg, Germany, and immunoenzymatic assay, Radom SPA via del Mare in 105 Panesia, Rome, Italy, respectively, to eliminate inter-assay variants. All samples for a particular assay thawed once the analysis in the same assay run. All samples were run in a duplicate with a mean inter and intra-assay coefficients of variance of 9.94 and 4.16% for serum TS, 4.9 and 5.6% serum for GH. The detection limits of the TS and GH were 0.515 and 0.083 ng milliliters, respectively. Lactate in plasma was analyzed using enzymatic using a YSI 1500 Sport, Yellow Springs, Ohio, USA. The CV for lactate was less than 5%. All samples from each subject were analyzed on the same day. Statistical analysis. Statistical evaluations of the data was accomplished by a repeat measure analysis for variance in the event of a significant F ratio. Least significant differences post hoc tests were used for pairwise comparisons. A criterion alpha level of P is less than or equal to 0.05 was used to determine statistical significance. All data were reported as means plus or minus SD. Results. The volume exercise per set for squat and bench is shown in figure 1 and 2 respectively. Training volume decreased over sets during 3 protocols. Total work performed comparison between groups P30, P60, and P120 revealed no significant differences. P greater than 0.05 and P60 3,603.81 plus or minus 816.05 kilograms, P90 4,175.50 plus or minus 939.89 kilograms, and P120 4,352.06 plus or minus 996.87. Figure 3. Blood lactate concentrations were significantly increased at T1 for 3 protocols, but no significant protocol differences were observed. Figure 4. The acute GH response in the exercise protocol can be seen in figure 5. Comparison within protocols revealed that during P60, GH concentrations were significantly higher at T1 and T30 when compared with T0, P is less than or equal to 0.05. During P90, GH concentrations were significantly higher at T1 when compared to T0. And during P120, the GH concentrations at T30 were higher than T0. P is less than or equal to 0.05. The GH comparison between protocols P30, P60, and P120 revealed that GH response was higher for P60 than for P120, but no differences was found between P90 and P120. The acute TS response to the exercise protocol can be seen in figure 6. During P120, the TS levels were significantly higher at T1 and T30 in comparison to T0. There were no differences among time points during P60 or P90. The TS comparison between groups P30, P60, and P120 revealed that TS response was higher for P90 and P120 than for P60, but no difference was found between 90 and 120. Discussion. Resistance exercise is the most effective way for achieving an acute increase in the concentrations of anabolic hormones, which in turn stimulates strength and muscle hypertrophy. High-intensity hypertrophic REs, when performed at multiple sets of 3 through 5 sets for each exercise, with short rest intervals 60 through 120 seconds and high repetition 8 through 12 repetitions, lead to acute hormonal response. The amount of time of acute hormonal response after RE may be related to gain of muscle strength and hypertrophy. The role of acute hormonal responses is very important because anabolic hormones, such as TS and GH, will increase protein synthesis in muscle cells. Therefore, investigation of endocrine gland through exercise activity may be a stimulant for the compatibility process of skeletal muscle cells and leads to an increase of contractile proteins. There has been more acute increase of GH and TS in multiple set resistance training programs, 3 sets per training, than with single RE program. Also, the RE protocol and average intensity with 10 RM load, high volume 3 sets of 10 RM, and each exercise with a short rest interval, 1 minute between the set, caused an increase in GH and cortisol concentration. It is inferred from the previous research that acute hormonal response related to RE is dependent on the kind of RE protocol that is affected by variables such as number of repetitions and set, load or intensity, frequency, and muscle volume involved. The present research, the young athletes have performed a 3 RE protocol, 4 sets times 85% of 1 RM to failure, maximum repetitions per set with different rest intervals of 60, 90, and 120 seconds. Therefore, the different programs was in the different rest intervals between sets, and because of using resistance training sets familiar RE to failure, we expected a different training volume related to the rest intervals. Also, different metabolic needs which these 3 RE protocols have are expected to cause different acute hormonal responses. The findings in the present study showed the total training volume in RE programs with rest intervals of 90 and 120 seconds between sets increased 20 and 15% more than that of the protocol with rest intervals of 60 seconds between sets. Although these differences were not statistically significant, they cannot be neglected because these differences might all affect measured physiological responses. Growth hormone and TS have been known as hormones involved in anabolic processes in muscle cells. Therefore, these hormones may instigate an increase in muscle mass. Binding of GH to its membrane-bound receptor initiates Janus kinase 2 signaling. Janus kinase 2 signaling activates phospholipid lynosol 3 kinase, PI3K. Because PI3K is proximal to the protein kinase B mammalian target of rapamycin, AKT-mTOR signaling, it is likely that the GH response to RE protocols translational effects efficiency and muscle anabolism by EIF2B activity and 4E-BP1 phosphorylation, resulting in enhanced translational efficiency and protein synthesis. For a review, see Spearing et al. The results showed that GH responses are different from the RE programs with rest intervals of 60, 90, and 120 seconds between sets. Serum GH concentrations immediately after heavy RE to failure with a rest interval of 60 seconds between sets was higher than RE to failure with a rest interval of 120 seconds between sets. However, 30 minutes after the training, no significant differences between these 2 protocols was observed. The greater increase was also observed in GH concentrations immediately after the RE protocol with a 60-second rest interval compared with a 90-second rest interval, but statistically it was not significant. No significant difference was also observed in the concentration of this hormone between 2 programs with rest intervals of 90 and 120 seconds. These findings are in accordance with those of Bataro et al. They observed a significant increase in GH concentrations in the RE protocol with a 30-second rest interval compared to 60 and 120-second rest intervals. Although in the present study, the maximum increase in GH concentration was observed in the RE protocol with 60-second rest, the difference may emanate from the difference in training intensity load in these 2 investigations. Because the present research has been used 85% 1 RM, which is heavier than the load used in Barreto et al. In addition, our findings are in accordance with Borghetti and Rahimi, who observed 15% meaningful increase in GH concentrations during an RE program, 5 sets with 10 RM, load in squat, bench press exercises, with 60-second rest between sets compared with 180-second rest. Corroborating these findings, Kraemer et al. Reported that performing the training with 10 RM with a 60-second rest interval between the sets led to a large increase in serum GH concentration compared to RE protocol with 180-second rest. In the same research, Kraemer et al. Reported that GH concentrations immediately 5 and 15 minutes after RE was greater in the protocol with 60-second rest between sets than that with the 180-second rest period between sets. Although the relative share of adjusting mechanisms for the increase in serum GH concentrations during heavy RE with this very short rest period is unknown and may be affected by glycolytic metabolic increases and acid-base changes. Previous research suggests these factors related to anabolic metabolism are involved adjusting control GH and that these factors may respond much to an intense resistance training program with short rest intervals between sets. Heikkinen and Parkkarinen observed a significant correlation between individual changes in lactate accumulation and GH response when two different strength exercises were combined, but did not measure changes in blood pH, but changes in blood lactate concentrations could explain differences in GH responses during 3 protocols. Also, previous research with restriction of blood flow during exercises showed that local accumulation of metabolic intermediaries such as lactic and hydrogen ion stimulation, the increase in GH. Corroborating this hypothesis, Gordon et al. Showed that alkalosis stimulated by sodium bicarbonate ingestion has decreased GH response during resistance training, although the real mechanism through which the acid-base changes stimulate GH secretion is not known correctly. It has been suggested that the hypothalamic hypophyseal axis is activated by muscle metabolic receptors signals. In line with the findings for GH, blood lactate concentrations increased during all 3 kinds of RE to failure, with greater responses observed in protocols of 60 seconds rest between sets than in 120 seconds between sets. Growth hormones are actually a family of hormones because more than 100 different variant forms exist in circulation. The specific biological activity of each GH variant awaits complete elucidation. However, acute RE dramatically affects concentrations of these GH variants. Additionally, Kraemer et al. Recently demonstrated that long-term training increases the biological activity of circulating GH molecular weight variants. Although our results showed that RE with a very short rest period instigates 20 kD GH monomer levels, the most frequently studied form, they do not solely responsible for adaptations to RE. In addition, GH exerts its function by eliciting IGF-1 production from the liver and or muscle, which stimulate muscle hypertrophy via PI3K and AKT-mTOR signaling. Additionally, IGF-1 stimulates the proliferation and differentiation of satellite cells. The findings of the present and previous research studies suggest that GH response to RE is dependent on short rest intervals between the training sets. Heretofore, it was suggested that training volume, number of sets, times number of repetitions, times amount of load is one of the determining factors of GH response. However, the findings of the present investigation do not confirm the suggestion because the RE protocol with 60 seconds rest between sets has led to the largest increase in serum GH concentrations. While it has had the least training volume. Moreover, Bottaro et al. Observed that the RE protocol with 30-second rest between sets elicits higher GH levels despite resulting in the lowest training volume compared to 60 and 120-second rest protocols. In the present investigation, the maximum training volume has been observed in the training program with 120-second rest. The results are in accordance with those of Bottaro et al.'s, Rahimi et al.'s, Willardson and Burkett's investigations, and it has been shown that these studies that with an increase of rest between resistance training sets, training volume has been increased meaningfully. The results presented here indicate several conclusions concerning the number of repetitions possible in an exercise session and consecutive sets of the same exercise to failure when rest periods were 60, 90, or 120 seconds in length. A rest period of 60 seconds results in less total training volume than a rest period of 120 because of the greater decrease in the number of repetitions to failure in consecutive sets with a 60-second rest period. This decrease in training volume in the 60-second rest periods is probably related to insufficient time to replenish anaerobic energy sources and neural drive and higher blood lactate concentrations, all of which result in fatigue. According to the results, the TS concentration was higher immediately after protocols with 120 and 90-second rest than after a protocol with 60-second rest between sets, but 30 minutes post-exercise, no meaningful difference was observed in TS concentrations among the protocols. In addition, meaningful differences in TH concentration during RE protocols with 90 and 120-second rest periods between sets were not observed. These findings are in accordance with those of Kraemer et al., who showed that higher intensity RE, 5RM, with large muscle groups and with 3-minute rest between sets elevates TS concentrations. Although circulating hormone concentration is one of the symptoms of hormone function, they are not solely responsible for adaptations to RE, and there are factors such as number of receptors and affinity of receptors that affect hormone function and subsequent adaptations in body tissue. Testosterone exerts its influence on skeletal muscle protein synthesis via androgen receptors, AR. Testosterone binds to and converts AR to a transcription factor capable of translocating to the nucleus and associating with DNA to regulate androgen-specific gene expression. Previous studies reported that training influences the number of androgen binding sites in skeletal muscle. The increase in ARs would lead to an enhancement of the sensitivity of muscles to circulating androgens. A significant increase in the number of ARs has been shown to occur after endurance and strength training and electrical stimulation in animal studies. Because the results were male resistance trained athletes and they prevalently trained with submaximal load, high repetitions, and short rest periods between sets, upregulating of ARs may have occurred in fast twitch fibers, and this led to low TS concentrations in a very short rest protocol. Additionally, like IGF-1, TS exerts some influence on muscles via satellite cells. Supraphysiological doses of TS increase satellite cell number in a dose-dependent manner and stimulate satellite cell proliferation and differentiation. Unfortunately, studies focusing on the effects of different rest periods between sets on TS concentration in resistance-trained men are lacking, making it difficult to compare our results. However, in terms of RE intensity, Rastad et al. Showed that the acute responses of TS was greater during the high-intensity protocol as compared to the moderate intensity protocol, and no meaningful differences was observed in luteinizing hormone, LH follicle-stimulating hormone, and GH. Linamo et al. Examined acute hormonal responses to maximum heavy RE, submaximal heavy RE, and explosive RE. They observed greater increase in GH and TS concentrations in maximum heavy RE compared with submaximal and explosive RE. Our findings showed that RE protocol with a long rest period between sets and greater training volume elicited an increase in TS concentration, but the possible mechanisms responsible for these changes were not measured in this study. However, previous studies suggest that exercise-induced elevations in TH are caused by mechanisms other than the normal LH stimulation of Leydig cells. Stress related to RE, reduced clearance, androgenic stimulated secretion, and lactate stimulated secretion, and homoconcentration have been suggested as other mechanisms for exercise-induced increases in TH concentration. Lactate stimulates TS secretion in Leydig cells from rats in vitro, and lactate infusions resulting in similar elevations in plasma TH concentrations are seen during exercise, have been shown to elevate TS concentrations in rats in vivo, and the present study significant differences were observed in mean blood lactate from pre to post exercise within protocols, but not between each protocol. Also, there was no correlation between individual changes in lactate and TS concentrations for either protocol. Therefore, this hypothesis that lactate stimulated secretion of TH was not confirmed by the results of the present study because the greater lactate accumulation observed during the 60-second protocol, which has the least TS concentrations as compared to the 120-second protocol, the possible role of lactate in stimulating TS secretions during exercise in men requires further investigation. In summary, the results of this investigation indicate that serum GH and TH concentrations were dependent on the length of the rest between sets in heavy RE protocols to failure. The primary finding of the study was that the patterns of GH and TS responses were dramatically different from the length of rest interval between sets in heavy RE, 4 sets of squat and bench press to failure using 85 of 1 RM. An RE protocol with a short rest interval between sets elicits greater increases in serum GH concentration compared to a long rest period, but acute TH responses were greater in the protocol with a long rest period and high training volume. There are few limitations of this study that warrant discussion. First, manipulation of the acute RE program variables, i.e. exercise choice, load, volume, rest periods, and exercise order dramatically influences the signaling responses and subsequent adaptations to RE. The direct influence of rest periods on mediating RE-induced muscle signaling responses is largely unexplored. Therefore, it is recommended that future studies evaluate the effect of different rest periods on signaling and response. Secondly, these findings are related to few numbers of anabolic hormones. Further investigations are necessary to determine more anabolic hormones and growth factor. Third, these findings are specific to the RE protocol that was performed to failure. Further investigations are necessary to determine if these findings are generalizable to the RE protocol, not to failure. Fourth, our findings are specific to the RE protocol performed at 85% 1 RM. It is unknown whether similar findings exist during RE protocols performed at different intensities. Additionally, our findings are specific to healthy resistance-trained men. Further investigations are necessary to determine if these findings are generalizable to other populations. Practical applications. In this study, we demonstrated that the rest interval between sets affects GH and TH responses and so could influence hypertrophic gains over time. During an RE session, a rest period of 60 seconds results in greater serum GH levels and less training volume than a rest period of 90 and 120 seconds. But the TS response was greater in the RE session with long rest periods. Short rest periods are typically recommended for RE protocols designed to maximize muscle hypertrophy because short rest periods augment the GH response when compared with long rest periods. However, short rest periods impair physical performance during subsequent sets, and over several weeks attenuate strength increase when compared with long rest periods. Of particular importance to the RE practitioner is that specific combinations of RE variables must be used to optimize the desired functional outcome: muscle strength, muscle power, muscle size, and muscle endurance. Therefore, it is recommended that short rest periods can be used to stimulate hypertrophy and that long rest periods are used to maximize strength gains. Acknowledgements. The authors are grateful to the subjects who participated in the study. The authors would also like to acknowledge Dr. D. Shikenhoslami Vetani for feedback on a related proposal of the study. They also thank Dr. F. Jen at the Laboratory of Endocrinology for technical assistance with the immunoassay procedures. Funding was provided by Azad University branch of Mahabad, Vice Chancellor for Research.